In the first video, we looked at how Desmos graphed parametric equations and saw that we saw motion. What I want to do is fill in the algebraic holes, stuff you will see algebraically instead of in terms of a graph, and then talk briefly about the 3D. Now remember, there we started by saying that the first time you saw parametric equations was probably on the unit circle. You just write down the definition of cosine. X is cosine t on the unit circle. Y equals sine t on the unit circle. And when you put that into Desmos, it actually graphs the unit circle, which is what we want. The algebraic stuff that's missing starts out with x squared plus y squared equals 1, which is the equation of the unit circle. We're going to see this a lot. When we see something squared plus something squared equals 1, what we're usually going to want to do is let that first something be cosine, the second something be sine, and we'll find ourselves writing down the parametric equations that we want. If I want to start with a circle of a different radius, say 2, I'm going to write down algebraically x squared plus y squared equals 4. If we want to find parametric equations algebraically for this, we're going to divide both sides by 4 and write this in standard form. So this is going to be x over 2 quantity squared plus y over 2 quantity squared equals 1. We let that first chunk be cosine. So I'm going to write down x over 2 is cosine, or x equals 2 cosine t. And when we have something squared plus something squared equals 1, I'm going to let that second chunk be sine. I can let y over 2 is sine t. Now I'm going to get y equals 2 sine t, which is what we did with Desmos, actually, when we try to make it twice as big. If I want a circle that's not centered at the origin, we can do that as well. I'll just change this one a little bit. The equation we're used to writing down from algebra would be something like x minus 3 quantity squared. How about, say, y plus 5 quantity squared? How about equals 16? We'll do that. Now, when we did this with parametric equations, to be a little bit careful what I do here. Remember what this does is it moves the center 3 to the right and down 5. And so what we did first is we made sure this had the right radius by making this 4 cosine t and 4 sine t. That way I have a circle of radius 4. And I moved down 5, which subtracts 5 from the y value. And then we moved it 3 to the right, which should add 3 to the x value. Now that's how we did it with Desmos. How do we do it here algebraically? We write it in standard form, so we divide everything by 16. So I'm going to get x minus 3 over 4 quantity squared plus y plus 5 over 4 quantity squared equals 1. We let that first chunk, since I have something squared plus something squared equals 1, I let that first chunk, x minus 3 over 4 equals cosine t. I saw that for x, I'm going to get x equals 4 cosine t plus 3, which is what I did when we did it with Desmos. But here we're just doing it purely algebraically. And I let the second chunk be sine. So I'm going to let y plus 5 over 4 be sine. I'm going to solve for y, so I get y equals 4 sine t minus 5, which is exactly what we did when we did it with Desmos. But we're going to have to see this a lot. Now, by the way, if you want to ask the question, how come I had to let the first chunk be cosine and the second chunk be sine? You didn't have to, right? We just want to take advantage of the fact that something squared plus something squared equals 1 is usually cosine squared plus sine squared. But if I wanted to let that first chunk be sine and that second chunk be cosine, we get simply a different parameterization of the same circle. In other words, we get a point that travels along the same circle, but it usually starts at a different point, and very often it goes in a different direction. So we can get circles that way. We can get ellipses exactly the same way. Let's talk about ellipses. A very first equation you usually see with ellipses is something like 4x squared, how about plus 9y squared equals 36. We know that's an ellipse because it's got two squared terms, but the coefficients are different. We write that in standard form. So we divide everything by 36 and rewrite. So I'm going to get x over 9 quantity squared plus y over 4 quantity squared equals 1. The reason we wrote that in standard form is because now I see something squared plus something squared equals 1. I'll let the first chunk be cosine. So x over 9 is cosine. So I get x equals 9 cosine t. I let the second chunk be sine. So I get y over 4 equals sine t. So I get y equals 4 sine t. And you get the kind of parametric equations that we actually saw with Desmos when we changed the coefficients. We can go a little bit beyond Desmos. Say I want a circle of radius 2. Say a circle of radius 2. How about in the YZ plane? Any center I want. How about I need x equals 0, and how about 5, 7, like this. Now, if I'm in the YZ plane, x is 0 the whole time, and so I can just put x equals 0, and that puts me in the right plane. If I want y equals something and z equals something, we know how to do this. If I make y equals cosine t and z equals sine t, that's going to be a circle of radius 1, whose center is at the origin. If I want to make it radius 2, I simply put a 2 out here. That makes it radius 2. I want the center to be at y equals 5 and z equals 7, so I just add 5 here, I add 7 here, and I get a circle of radius 2 in the YZ plane. So basically, I just had to treat y like something or z like something. We can write down the equation here if we want, right? But we would need more than one equation. Anyways, so we can get a circle. We can put our circle anywhere we want to. The only other thing I want to talk about, and you should probably, hopefully, saw this in your Calc 2 or your Calc 1 class, but only in 2D, and we want lines in space. If I want lines in space, what we want to do is define a line between 2 points. So I'm going to have a starting point. How about, okay, we'll do this first. Let's do an example first. I say I want to start at the point 1, 2, 3. I want to add at the point, end at the point, say 5, 10, 20. Now, how do we do this? Well, what I'm thinking is, right, 1, 2, 3 is a point. 5, 10, 20 is a different point. And what we want is a line that includes 1, 2, 3. But to get to any other point on the line, you have to add a multiple of that vector between them. So let me write down the vector between them. I'm just going to call it D for direction vector. And what I'm going to get is 5 minus 1, that's 4. And 10 minus 2, that's 8. And 20 minus 3, that's 17. And so I can write down equations for x, y, and z. I know I want to start at the point 1, 2, 3, so I go 1, 2, 3 like that. And I know to get to any other point on the line, I add a multiple of 4, 8, 17, right? So I want to add any multiple, so I'm going to use t for the multiple of 4, 8, 17, which means that x is going to be 1 plus 4t, y is going to be 2 plus 8t, z is going to be 3 plus 17t. But like I say, this generalizes something you saw in your Calc 1, Calc 2 parametric equations, but it has a wonderful property that physics really wants, right? If you write it down like this, so you have the starting point here, and you use the displacement vector to be the direction of the line. When you plug in 0, you get the starting point. When you plug in 1, you get the ending point, and they really, really, really want that. So when we're actually going to find the equation of a line between 2 points, this is the way we're going to write it, and this is the way they're going to want us to write it. All right. Finally, if I write down x equals cosine t, y equals sine t, and I add something like z equals 5, right? What do I have? Well, I have a unit circle that's simply 5 units up, right? where the plane looks like this. That's great. If I make the z equals 15, it just moves it up 15 units. Not a big deal. That's not new. We just talked about that. But something that's very cool is what happens if z equals t. Right? I'm going to think of this in terms of motion. From above, where I can't see z at all, I'm just going to see something going around in a circle over and over and over. But z is actually increasing. So z starts at 0, but from above, it's going to look like a circle. And so what you're going to get is something that just goes like that. What we have here is the the equations of what's called a helix. We can get a lot of other cool motion as well. And you should look at what we have, and you should play with it.